Okay, good morning, everyone. Let's get into our examples for Thevenin and Norton. Very important topic. Again, as I stated previously, 30-point problem in the final exam. Okay, so today I'm going to go over two examples. Section 4, example 1. We'll start with Thevenin resistance. Okay, in the circuit shown here, we have five sources and 4 resistors, and we are simply asked to find the equivalent resistance between terminals A and B. Thevenin equivalent resistance between A and B. So RTH is the unknown value. Okay. So when it states find it between a particular pair of terminals, you do is you analyze the circuit from the perspective of those terminals. So we need to find REQ between terminals A and B. So as the first step, we need to do a correct problem setup. The problem setup for a resistance, of course, is to remove all the sources in the circuit so that all we are left with in the circuit is a bunch of resistors. And then we can try and reduce those resistors down to one single resistance. So let's, in order to remove all the sources in the circuit, we reduce all independent sources to 0. So first step is to reduce all independent sources to 0. And then I would redraw the circuit. Now I'm drawing this for explanation purposes. Students do not have to draw it this way. I'm showing the places where the sources were connected. But again, you do not have to draw it this way. This is I2, I1. Current sources are, of course, open. V1, V2, and V3 are shorted out. I have R1, R2, R3, and R4. Okay. We reduce all independent sources to 0, meaning replace a voltage source with a short circuit and current source with an open circuit. Then redraw the circuit. Make sense? Right? Now, again, as I said, I draw this for explanation purposes. You can draw it like this, or you can simply draw it like this. Either one is fine. R1, R2, R3, R4, terminals A and B, and we need to find REQ between those terminals. Okay, 10-second pause while you write it down, think over it. Let me know if you have any questions. Any questions? Easy enough? All right, so what do we do for REQ? We go back to the beginning of this chapter, chapter 2, where we take a large network of resistors and reduce it down to one single resistance. We start at the farthest end from our terminals, right? We start at the farthest end of our terminals and we move towards those terminals. So the farthest end of our terminals, we have R1. The next resistor up is R2. What is the relationship between R1 and R2? They are in parallel. So REQ, starting at the farthest end, gives me R1 in parallel with R2, which is then in series with R3, absolutely. And then finally, parallel with R4. And that's it. If we had values at this point, we simply plug in the values and calculate. And that's our REQ or RTH, Thevenin resistance. All right. The calculation, the equation, of course, it's not something new, but the setup of the problem, which is reducing the sources to zero, that is something we talked about previously for superposition, and we continue the application to find RTH. Now, this only works if the circuit connection is reducible, right? The only examples we see in this class, all of the circuits are reducible. But in real life, many of the circuits that we analyze, that we use, are not reducible. Obviously, we can, if you want to do a practical measurement, we simply take a meter, connect it to our terminals, and we can measure the Thevenin resistance that way. But if you want to calculate manually, then all circuits may not be reducible. And in those cases, we have to find Thevenin voltage. Then we find the Norton current. We apply Ohm's law, V over I, and that would give us the Thevenin resistance. That is one reason why we need to find all three quantities, or at least have the capacity or capability to find all three quantities. It's not always possible to reduce a resistive network down to one single resistance manually. All right. Okay, any other questions? Problem setup? Anything? All right, then we move on to example 2. Example 2, and this is a very important point, asks us to find the Thevenin and Norton equivalent circuits if the 2 ohm resistor represents the load. And so at this point, I will take you back to that summary slide, to that first point right there. If the question states, if the problem statement has this phrase, as seen by a particular component, or says represents the load, or it says represents the second circuit or the follow-on circuit, they all mean exactly the same thing. Okay, as seen by a particular component, or if it represents the load, or if it represents the second circuit, it all mean the exact same thing, that that particular component should not be part of your analysis. Okay, it's the same thing as me asking how many people are in this room, right? If there are 30 students in this room, I can see that as seen from my perspective, there are 30 people. But if someone says how many people are in the room, it's 30 plus 1, 31. Make sense? But if the question is as seen by me, I have to remove myself from the count. It's only 30 people. So if it's as seen by a particular component, that component is not part of your analysis. Now, for explanation purposes only, this is what I'm going to do. I will draw the circuit without the 2 ohm resistance. You do not have to draw this down or write this down. This is only for explanation purposes. The 2 ohm resistor is not part of the analysis, and so 12 ohms, 6 ohms, and 4 ohms with a 30-volt source, and my terminals of analysis are A and B. This would be the same thing as saying analyze the circuit between A and B, or find the Thevenin and Norton equivalent circuits from terminals A and B. Okay. Again, this is for explanation purposes. It's not something that you have to draw out. So this would be considered as the original circuit. You analyze it 3 times, 3 separate times. VTH, RTH, and IN. Redraw it 3 different times to find, well, you perform 3 separate analyses to find the 3 quantities. So far, so good. Again, this is not something that you have to draw out in a quiz or in an exam. Okay. So let's begin. RTH. Let's start with the first and the easiest, RTH. So RTH, again, reduce all sources, all independent sources to 0. The only independent source in here is that voltage source, and I will replace it with a short circuit. And so all I'm left with in the circuit are 3 resistors, and I have to find Req between terminals A and B, right? 12 ohm resistor. The 2 ohm resistor is not part of the analysis. We simply find Req between those open terminals. And then what do we see? Starting at the farthest end, I have the 12 ohm resistor in parallel with the 6, which is then in series with the 4 ohm resistor, right? 12 in parallel with 6, in series with the 4. So this is 72 divided by 18 plus 4. So Req is 8 ohms. Therefore, my Thevenin resistance RTH is also 8 ohms. Any questions? Again, rather straightforward as far as circuit analysis goes. Can't get any simpler. Make sense? Right? Again, the calculation part comes later, but the problem setup is the most important thing. Okay, if the problem setup is incorrect, then doesn't matter what analysis you do, your answer is going to be incorrect. Right? Any questions? Any questions at all? Is the problem setup clear? Okay, let's move to Thevenin voltage. So VTH. Remember that all important point. Once you find one quantity, you forget about it. This has no bearing on VTH or IN. Okay, you forget about it. It's blank slate. We redraw the circuit. This time the source is back in there, of course. And we simply analyze it to find the open circuit voltage at the output terminals. This is A, this is B. Remember the polarity, the reference direction, the reference polarity we take for the Thevenin voltage analysis, plus up top, minus at the bottom, and we find the open circuit voltage between those open terminals. Okay, the 2 ohm resistor is not part of the analysis. So we take the original circuit, we remove the 2 ohm resistor, and we analyze the circuit between terminals A and B. Setup of the problem, again, I'm repeating the same thing. The problem setup is the most important thing. If the setup is incorrect, then your analysis doesn't matter. This also brings up a very important and interesting concept in circuit analysis. So let me begin by drawing out the current direction. So the 30-volt source supplies current. Obviously, current for a source goes from minus to plus. And I will call that IL. Now, current flowing through the 12 ohm resistor is the exact same thing as the current flowing through the 30-volt source, IL. What happens when it hits this junction in the middle? Normally, I would say it splits, but current needs a pathway to flow through. The 4 ohm resistor is not connected to anything. So all of that current is going to flow down the 6 ohm resistor. No current flows through the 4 ohm resistor. If no current is flowing to the 4 ohm resistor, again, because it's a dead end street, it's left hanging in the open. There is no closed pathway for the current to flow through. That means that current I through the 4 ohm resistor is 0. Hence, the voltage across the 4 ohm resistor is 0. And we can conclude that the voltage at point A is the same as the other end of that resistor. So again, the concept is if the resistor is left hanging in the open, there is no current flowing through there, and both ends of the resistor have exactly the same electric potential. Okay, same electric potential. And you can do this in a lab. Next time you're in a lab, you can take the circuit, connect a couple of resistors, doesn't matter what the value is, leave one resistor open, and you measure the voltage with reference to B, obviously, at both ends of that resistor, and it should be exactly the same. So VOC between A and B is exactly the same as the voltage across that 6 ohm resistor, because the bottom node is common. Okay, this is still B. This is also B, right? It's the exact same node. The voltage across the 4 ohm resistor is the same as the, voltage across A and B is exactly the same as the voltage across that 6 ohm resistor. I can redraw the circuit in this manner. So I have a 30-volt source. This is 12 ohms. This is 6 ohms. This is 30 volts. I have total current IL flowing through here. IL also continues to flow through the 6 ohm resistor. Nothing goes down 4 ohms. And so AB plus minus VOC, exact same potential across that 6 ohm resistor. And now you can see the same current is flowing through 12 and 6, then they are in series. It's a one-step answer. You have voltage being applied to a series connection of resistances, and so I can get my answer by applying voltage division. From voltage division, I can write that VOC is a fraction of 30 volts, and the fraction is given by 6 divided by 12 plus 6, which gives me 6 over 18, 1/3. 1/3 of 30 is 10 volts. And so my Thevenin voltage for this circuit is 10 volts. Does that make sense? The actual analysis will differ. That depends on the circuit, and it also depends on the individual person. Every student will think differently, and so the analysis technique they choose would be different. But the problem setup has to be the same for everyone. The problem setup obviously would not be different. The analysis technique after that is up to you. The steps make sense. Yes. You can, and that's one of the point. That's usually how many textbooks teach and how many instructors also teach in class. But it is more important. So I have three reasons. One reason is, of course, if the circuit is not reducible, we don't have RTH. So we need to find IN in order to find RTH. If it has a dependent source in there, again, if a dependent source is in there, we cannot reduce it to 0. We cannot find RTH. So we have to find IN, apply Ohm's law to find RTH. And even more importantly, you need to be able to verify your answer at the end by applying Ohm's law, all three. If you find two quantities, right, as we have here, VTH and RTH, if one of them is incorrect, then you end up with 2 incorrect answers out of the 3. Make sense? Right? So we need to be able to analyze the circuit 3 times and find RTH, VTH, and IN independently. All right, so let's move into the analysis for IN, Norton. In IN, let me get rid of this. Okay. What do we need for IN? We need a closed pathway for the current to flow through. In this case, we're analyzing for the 2 ohm resistor. So we need a closed pathway for current to flow through that 2 ohm resistor. So we place a short circuit in its place. And this is A, this is B, and take note of the current direction. ISC is flowing down this way. Current needs a pathway to flow through. So if we want to analyze and find Norton current, we need to have a short circuit wire between A and B. Note, the 2 circuits are not the same. For Thevenin voltage, we had open circuit. Again, voltage can be measured across 2 points. Obviously, if you measure the voltage in this circuit, it's going to be 0, whereas here the current is 0. So 2 different circuits. The results you obtain from one do not have any bearing on the analysis for the other 2. Okay, so if you look at this circuit, what do we see? We have a short circuit wire going from point A to point B. And because of that short circuit wire, that 4 ohm resistor is now in parallel with a 6 ohm resistor. So I can redraw the circuit like this. And because it's in parallel, I can do this. This is 6, this is 4, 30-volt source, 12 ohm resistor. And then this time I'm going to say the total current in the circuit is IZ. IZ comes down from the 12 ohm resistor and it splits in 2. Some of it goes down this way. Some of it goes down the 6 ohm resistor. Make sense? Simply redrawing the circuit in a way that makes sense to me. You can redraw the circuit as many times as you want until it starts making sense to you. Let's look at the circuit above. What can we see about ISC, the short circuit current? If I extend ISC, what do I see? What can we conclude? What can we conclude about ISC? Exactly. ISC, the short circuit current going from point A to point B, is the current that is flowing from the, not from, is the current that is flowing through the 4 ohm resistor. So we simply find the current flowing through the 4 ohm resistor, and that will be ISC. One other point is that 6 and 4 ohm resistor are in parallel. So they share the same voltage. I'm going to label it as VZ. VZ. Okay. So VZ is measured from here to here. and it's also measured across the 6 ohm. Again, both are in parallel. Doesn't matter how many components you have in parallel, the voltage always remains the same. So there are a couple of different ways I can analyze this. I can, as a first step, I'm going to reduce the 6 and 4 ohm resistances. So this is 24 divided by 10, gives me 2.4 ohms. Right, 6 and 4 in parallel, reduce it to one single resistance. That is 2.4, and 2.4 is in series with 12. I can apply voltage division to find VZ. Yeah, I can apply voltage division to find VZ. So it's fraction of 30 volts, and the 30 times 2.4 divided by 2.4 plus 12. So this gives me, what does it give me? Let's see. 2.4 divided by 14.4 times 30. 5 volts. VZ is 5 volts. I can apply Ohm's law and find the current to the 4 ohm resistor. That would give me ISC. I'll take a pause while students think over this. Let me know if you have any questions. Okay. Yes. We'll do that. I'm going to do that also. I'm going to show you multiple ways of solving the exact same problem. So again, the exact analysis technique depends on the individual person. And in real life, obviously, we will want to make sure that our analysis is correct. So we would solve the exact same problem multiple different ways until we arrive with the same answer with all methods, which is also something I strongly recommend to students, whether it's mesh current analysis, node voltage, or superposition. You have solved examples in class as well as the homework problems. So as practice to make yourself better at circuit analysis, you solve each example with all 3 methods and see if you can arrive at the same answer every time. Okay. So in real life, that principle holds true. You always take a problem and solve it multiple different ways to arrive at the same answer to verify your answers. In this case, I can write ISC is simply 5 divided by 4, which is 1.25 amps, which from Ohm's law, we already expected, right? If our answer was incorrect, they would not match up. In this case, they do match up. So if I wish to apply current division, I need to find IZ first, right? I need to find IZ. IZ is simply, so I'll put a line through there. IZ would be given by 30 volts divided by 12 plus 2.4, and that gives me 2.0833 amps. Okay, IZ, which is the total current being supplied by the 30-volt source. That's the current flowing through the 12 ohm source. And then the 12 ohm resistor. And the 12 ohm resistor, after flowing through the 12 ohm resistor, it hits the parallel combination of 6 and 4, and it splits in 2 parts. Current is being divided. I can apply current division to find ISC. And that would be a fraction of IZ. The fraction would be given by REQ of 6 parallel 4 divided by 4. So this would be 2.0833 times 2.4 divided by 4. And that still gives me 1.25 amps. So you could analyze this exact same circuit two different ways and arrive at the exact same answer. And so my Norton current (1.25 amps). Okay, think over it. Let me know if you have any questions. Any questions at all? Do the steps make sense? Does the methodology make sense? Again, the analysis technique is different. That is something you can review after, after class or outside of class. But more importantly, students should understand how to set up the problem itself. And that's where most of the students have errors. Because if the problem setup is incorrect, the analysis doesn't matter if your analysis is correct from that point on. Any questions? Okay, we'll verify our answer. So VTH should be equal to IN times RTH, which is 1.25 times 8, gives me 10 volts, which is what I found from my VTH. Answer is verified. My Thevenin circuit the final Thevenin circuit should have a voltage source This is VTH of 10 volts. This is RTH of 8 ohms. These are my terminals A and B, where the 2 ohm resistor is plugged back in. The original problem has a notation of Vx as the voltage across that 2 ohm resistor. The question asked is, what is the voltage across Vx? Well, we can apply voltage division and simply find the answer as one step. The VTH times 2 divided by 8 plus 2. In this case, it's 2 volts. Similarly, our Norton circuit, our final Norton circuit should have a current source Then we have our terminals A and B and the 2 ohm resistor connected. This is RTH, again, 8 ohms. This is IN, 1.25 amps. So those are our final circuits. If I wanted to, I could find the current flowing through the 2 ohm resistor by applying current division. One important point, note the direction of the Norton current of the source. ISC in the analysis is going down from A to B, right? That is the current that is flowing from A to B, which is where the 2 ohm resistor was connected. So this current direction matches the current direction for ISC. Actually, it's not ISC, direction. Okay, current direction is from A to B going downwards, and A to B is where 2 ohms was connected. So if you logically follow that pathway, then Norton current has to be going up. Does that make sense? Right? A and B, this is where we analyze the circuit. ISC was going from A to B, from top to bottom, from A to B. So if that's the case and my current is going down from the top, I extend that current, and then IN, my current source, is going up. It also relates to the Thevenin voltage. Thevenin voltage is a plus up top, minus at the bottom. Source will always supply, so it goes from minus to plus. Okay, so keep those in mind. All right, questions? Any questions at all? No other questions? Well, we'll end class here today. That's the end of example 2. I'm going to record the solution for example 3, and I will post it online. Most likely, I want to get it done today, but I have a lab from 3 to 6 and office hours in between. So if I get it done tomorrow morning, it's be tomorrow afternoon. I want to do it by today afternoon, before 3 o'clock if possible. I will send out an announcement and post it on Canvas as soon as it's available. In the meantime, review examples 1 and 2. You can take a crack at example 3 by yourself if you wish. The homework was due this Friday. I'll push it back to like Sunday night, because the quiz for Monday will be on Thevenin and Norton. I want all students to do as well as they can, and so I want to make sure they're prepared the best. Okay, and I'll be available in my office today, tomorrow, Friday, Saturday, Sunday. Well, Saturday, Sunday over Zoom. If you have any questions, but again, I want the students to be, best prepared for quiz on Monday. All right. So we have a few minutes. I'm going to end class here today. If you have any questions, I'm around. Otherwise, I'll be back in my office later this afternoon. Right. I will see you all on Friday.